push the buzz like rush. Whatever tunes your knees to mush, they hit the lift. Even if you gotta sift through the shit to get to the twist, the smile I hide like it's your very last line. Can never get another try. Do it loud, do it for the loud, for the here and now.
Human vision relies on a duplex retina, comprising two types of photoreceptor cells. Rods are primarily responsible for dim light scotopic vision, and cones are primarily responsible for daylight photopic vision. For all known vertebrates, scotopic vision is monochromatic, since there is typically only one class of rod cell. However, the presence of multiple cone classes contributing to photopic vision enables color vision during daytime conditions. Dichromatic color vision is enabled by two types of cone cells with different spectral sensitivities and the neural framework to compare the excitation of the different cone cells. The resulting color vision is simpler than typical human trichromatic color vision and much simpler than tetrachromatic color vision. A dichromatic color space can be defined by only two primary colors. For comparison, a trichromatic color space requires three primary colors to be defined. However, even when choosing three pure spectral colors as the primaries, the resulting color space will never encompass the entire trichromatic individual's range of sight. Here is a picture representing what a prey animal sees when viewing a tiger in the wild. And here is a picture how us humans see them. The color vision of dichromats can be represented in a two-dimensional plane, where one coordinate represented brightness and the other coordinate represents hue. This means that dichromats see white in a rainbow. Dichromacy in humans is a form of color blindness. Normal human color vision is trichromatic, so dichromacy is achieved by losing functionality of one of the three cone cells. There are three standard color-detecting cones in the retina of trichromats. Blue, green, and red can pick up about 100 different gradations of color. If each detector is independent of the others, the total number of colors discernible by an average human is about 1 million to upwards of 2.3 million. Dichromats have a significantly higher threshold than trichromats for colored stimuli flickering at low frequencies. At higher frequencies, dichromats perform as well as, or better than trichromats. This means such animals would still observe a flicker instead of a temporally fused visual perception. Until the 1960s, popular belief held that most mammals outside of primates were monochromats. In the last half-century, however, a focus on behavioral and genetic testing of mammals has accumulated extensive evidence of dichromatic color vision in a number of mammalian orders. Mammals are now usually assumed to be dichromats, possessing S and L cones, with monochromats viewed as the exceptions. The exceptions to this rule of dichromatic vision in placental mammals are Old World monkeys and apes, which re-evolved trichromacy, and marine mammals, both pinnipeds and cetaceans, which are cone monochromats, that is, see in shades of gray. New World monkeys are a partial exception. In most species, males are dichromats, and about 60% of females are trichromats. But the owl monkeys are cone monochromats, and both sexes of howler monkeys are trichromats. So given the complexity of vision across different species, and even differences within the same species, who knows what visual capabilities a Sasquatch can have when it comes to identifying game cameras? Is it just visually perceptive to them? Are they sensitive to the electronics? The IR light? Do they watch you put them up? The brain translates light into color. Light receptors within the eye transmit messages to the brain, producing the familiar sensation of color. The retina is covered by millions of light-sensitive cells, some shaped like rods and some like cones. And it's these receptors that process the light and then send this information to the visual cortex. Rods are mostly concentrated around the edge of the retina and transmit mostly black and white information. Cones transmit the higher levels of light intensity that create the sensation of color and visual sharpness. These cells, working in combination with connecting nerve cells, give the brain enough information to interpret color. Here is where the smoothness of a plastic camera container may easily be seen next to a very porous surface, like tree bark. Think of atoms like bricks in a wall, chemical compound. Imagine throwing a ball into the wall. If the wall is smooth or has sharp corners, the ball may jump back in different directions. However, if the wall is filled with holes, the ball may go through the wall or get stuck in one of the tricky corners, respectively. Same with every surface when light hits it. The surface may reflect the light back. It can absorb light or just let it pass through.
For the heat